Okay, great. Okay, well, welcome everyone to another MCRN Colloquium. Today we're lucky to have Professor Ian Grooms from University of Colorado Boulder speaking. So he got his PhD from University of Colorado Boulder, I think in 2015, and then you spent some time at the Courant Institute as a postdoc before returning to CU Boulder and then getting tenure there in 2022. His research interests encompass subgrid scale parameterization for global ocean models, the development of new data assimilation methods, which he'll speak about a little bit today, and the theory of geophysical fluid dynamics and turbulence. So very much looking forward to the talk, and with that, please take it away.
Thanks, Christian. I think what I sent you for a little bio had a typo. My PhD was 2011.
Oh,
so
sorry.
That's my fault. Yeah, I started here in 2015, but that's all beside the point. So thank you for the invitation. Happy to be here. I can't see anyone on my screen, so I think, we can be informal. If anyone has a question, just speak up, interject, or we can talk at the end if anyone has questions. So I'll briefly say this is work that I'm doing with a student, Kate Bowden, who's a PhD student in applied math at CU, and we're grateful for NSF funding. So let's see, there we go. I'm going to start with background. It's actually going to take me a while. If you see my dots up at the top, everything is background really until you get to like here. So there's going to be a lot of background. But I think it kind of deserves background because I'm approaching the DA problem from a pretty different perspective from what's traditional. Not necessarily a new perspective, but just not one that people are maybe very familiar with. So I'm going to start with some background relating regression and data assimilation. And I'm actually not going to use regression, but I think it's relevant for the big picture. So from my perspective, I'm doing ensemble data assimilation. I appreciate that there's variational, but I'm just looking at ensemble right now. And the goal of an ensemble data assimilation scheme, from my perspective, is to generate an ensemble that is drawn from the Bayesian posterior distribution. And then with that, you can do whatever you want. You can estimate moments. But that's what I think is the goal, to produce this analysis ensemble. And the Bayesian posterior that we're targeting, it's a conditional distribution. And so sampling from a conditional distribution can be done using regression, but that's not how we usually think of regression. So I'm going to start with a little background on that. So standard notation, X is the state, Y is the observation. I've got a subscript N because I've got an ensemble of both, and a superscript F for forecast. And now, stepping back from our usual data assimilation, you can say, what if I want to predict the state from the observations? I've got observations and I want to predict what the state is. You could set up a simple linear model. So this is a simple linear regression model. Beta 0, beta 1 are your regression coefficients. Eta is your regression residual. And now we have data. So we don't know what the regression coefficients are, but we can estimate them. We do that by plugging our ensemble members into the simple linear model here. And then you can just fit using least squares. So we try to minimize the t-norm of the residuals. That's a standard thing to do. I'm actually going to, in order to make contact with more traditional data assimilation approaches, I'm going to split out the problem of finding the two coefficients separately. So I'm going to take the ensemble mean of this equation. Get this guy. I'm going to take the ensemble mean here, which gives me that equation. And then I'm going to look at the perturbations, and that gives me this equation. And now in the second equation, I can just estimate the beta 1 coefficient by itself, this regression coefficient. So I'm going to take all of my perturbations X, stack them as columns of a matrix X, all my perturbations Y, stack them as columns of a matrix Y, and then the simple least squares solution for this regression coefficient beta 1 is XY plus, where plus is the pseudo inverse. Okay, then you plug that back in. Once you have your estimate for the beta 1 coefficient, you plug it back into this equation, and that gives you an estimate for the beta 0 coefficient. So there you've got your two coefficients. And you could then use this to predict from the observed value of y, right? So I've set up a regression model, and now we estimated using our ensemble of y values, but now we could plug in the observed value of y and then predict a value of x. But if you're doing that, if you're just predicting with regression, which is what we usually do, you're not sampling from a conditional distribution, which is what we want to do. So how can we move from just predicting to conditional sampling? So the next ingredient is to assume homoscedasticity, which is to say we assume that the regression residual eta is not a function of y. And then with that assumption, we can go to conditional sampling. And here's a little illustration of how that works. So I've got, this should be y on the bottom. I just recycled an image that had z, but it's y on the bottom axis. That's the predictor. X is the response. My blue dots are my forecast ensemble. Black line is the regression line. The dashed line is the observed value of y. And we could predict the value of x using the observed value of y, just using the regression line. That gives you the red dot. But really, we don't just want to predict, we want to sample, which means we want to sample from the distribution along this dotted line. And a simple way to do that is to just say, well, I've got a bunch of samples of the residual eta. That's the distance between the blue dot and the black line from the forecast. And now to sample on the dotted line, I just take the regression prediction and add a sample from the residual. And since the residuals don't care where you are on the horizontal axis, I could just reuse the ones from the forecast. And if you do that and you put it all together, that's just exactly the perturbed ensemble Kalman filter. Well, almost exactly. So this matrix here is the Kalman gain matrix. It's not exactly the same ensemble approximation to the Kalman gain that we usually use, but it is just a different ensemble approximation. As the number of ensemble members goes to infinity, this matrix and the usual one both converge to the same Kalman gain. So that's a connection between using regression and doing ensemble data assimilation. Okay, that was review, regression. Now I'm going to introduce a little more background. So you can do ensemble data assimilation in 2 steps. And so for the sake of exposition for how this 2-step process works, I'm going to assume you got the standard observation model here. And what the first, so I'm going to define z to be the observations, h of x, but without any perturbations. So unperturbed observations. It would be common to denote this by y, but it would be an abusive notation because y and z are not the same thing. And I need to not abuse notation in order for this to make sense. So I've got a new letter z here. So now with that notational background in the top half of the slide, the bottom half of the slide tells you what happens in the first step of 2-step data assimilation. In the first step, you just do an analysis in observation space. So you produce an analysis ensemble in observation space. And you can use anything you want for that. Ensemble Kalman filter, particle filter, Gaussian mixture, whatever you want. Okay, so that's the first step. Of course, you can't stop there because we're not just trying to estimate what happens in observation space. We're trying to estimate x. So there has to be a second step. And in the second step, you use your updated ensemble in observation space to produce an updated ensemble in state variable or model space. How do you do that, though? There's sort of lots of ways of doing this. So Jeff's paper from 2003 here, his EnKF paper, it's not, what's often cited as the EnKF paper. This is the first 2-step filter. And what he does in this second step is he uses regression to do conditional sampling of the state variable given the observations. But it's not the y observation, it's the z observation. So not the perturbed observation, but the unperturbed observation. And then if you do that, it ends up just being an ensemble Kalman filter. You don't have to do that, though. So in my 2022 paper down here at the bottom, I showed that what should happen in the second step is you're conditionally sampling from the state given the unperturbed observations. And if you can do that correctly by whatever algorithm you want, then the analysis ensemble that you produce over here will be drawn from the true Bayesian posterior. So I think what I contributed in the 2022 paper is sort of a mathematical framework to support and generalize what Jeff invented in the 2003 paper. So that's introducing the idea of conditional sampling in this second step. And previously, people used regression. I'm actually not going to use regression. Okay, that's background. So I'm interested in CICE data assimilation. And I'm going to use a two-step approach to do CICE data assimilation, ensemble data assimilation. And my first step is going to be in observation space. And I'm going to do serial processing of observations. So my observation space is just going to be scalar. And because it's scalar, I'm not constrained to use an Ensemble Kalman Filter. I mean, I can do anything I want to for my Bayesian analysis in observation space. And if it's low dimensional, there's lots of non-Gaussian things you can do. So for the first step in observation space, I'm going to do a transport-based approach. So the idea for this kind of thing goes back to Jeff's rank histogram filter from 2010. What that rank histogram filter does in retrospect is described by this equation here. So you take your forecast ensemble members, you then apply some function capital F. That function is the forecast CDF. So it's the cumulative distribution function of the forecast in observation space. You apply that, that moves you this way, up here to over there. Now you're between 0 and 1 because the CDF goes between 0 and 1. And then next you apply this function here, which is the quantile function. It's the inverse of the CDF, but it's the analysis CDF in observation space. And then that pushes you back down to here. So you've now updated your ensemble in observation space. This is essentially a composition of a probability integral transform. That's the first part, with an inverse sampling transform. That's the second part. You can think of this as a transport from the prior to the posterior. Anything that does this, so Jeff's filter with rank histogram was the first one to do this. But there's lots of ways of doing it because we don't know what the forecast CDF and we don't know what the analysis quantile function are. You have to estimate them from the ensemble. And because there's lots of different ways of estimating these functions from the ensemble, there's accordingly lots of different filters in principle that could do this. The rank histogram filter is just the first one. Jeff has a series of 3 papers over the past few years that calls this type of approach Quantile Conserving Ensemble Filters. So I'll adopt that name too. So for CICE, this is what I'm going to do, but there's lots of ways of doing it. So I'm going to develop a specific way of doing it. So I start by modeling the prior PDF in observation space, just a scalar, because I'm doing serial assimilation. And I'm going to allow the observed variable to be bounded. So maybe it's bounded between 0 and 1. But the PDF that I'm going to represent is not going to be a smooth PDF. It's going to have Dirac delta distributions on the boundaries, or it's going to allow for there to be non-zero mass, probability mass on one or both boundaries. So that's deltas on the boundaries, and then in between the boundaries, you have a smooth PDF. I estimate this distribution using kernel density estimations. It's just straightforward kernel density estimation. If you get the standard book on the subject, I've only used basically methods from there, except that there are boundary corrections to kernel density estimation, and those I've pulled from some other papers in the 90s. So these are basically just standard approaches to estimating a PDF, and I've inflated so that I'm allowed to have, half my ensemble members be on the boundary if I need that. Once I've got that, I need a CDF which is the integral of the PDF. And then I need an analysis CDF, which is the integral of the likelihood times the PDF. Both of those integrals I just do using quadrature. And then I need to invert the CDF here, and I just do that using root finding. So basically off-the-shelf sort of numerical scientific computing type of tools. So the method is described in this paper that came out last summer. And I really want to focus on the second step in this talk, so I'm not going to spend much more time about this. It is implemented in Dart. I've implemented it in Dart, and so it's available in the main release along with all the other filters. Before I move on, I want to briefly advertise. With this filter, because it's one-dimensional, you can actually test it in a way that we don't usually test data assimilation schemes. So what I did in the paper is set up multiple test problems where I know exactly what the prior is and exactly what the posterior is. And then I sample my forecast ensemble from the prior, and then I apply my my filter, my one-dimensional filter, to produce an analysis ensemble, and then I test the hypothesis, the null hypothesis. Is this analysis ensemble drawn from the true Bayesian posterior distribution? And if you reject the hypothesis, then it's a bad filter. And if you fail to reject the hypothesis, most of the times that suggests that you're doing well. So this figure I'm not going to explain because I don't have time, but it's one of many figures in that paper, this paper from 2024, where we basically set up a bunch of test problems and test various filters to see if they're actually sampling from the true Bayesian posterior. And this new method that I developed does pretty well. It's not perfect. It doesn't always, do well, but it does quite well. So that's what I'm going to use for my first step for CICE data assimilation. That's all background. Now I'm ready to talk about CICE. Maybe I should pause and see if there's any questions before I get into the CICE part. Okay, if you do have questions, just unmute and say something. Otherwise, I'll keep going. All right, so CICE. One of the main difficulties of data assimilation for CICE models, probably not the only difficulty, but one of the big ones, is the constraints that the model variables have to satisfy. In particular, in a CICE model, you've got some grid. Maybe it's a quadrilateral grid like in the CICE or CIS models. Maybe it's a triangle grid like in NextSim. But you've got a grid, and on each grid cell, you keep track of an ice thickness distribution. So for one grid cell, you say some fraction of this grid cell is covered by ice and the other part is covered by open water. So like maybe this part up here is open water and the rest of it is ice. But then furthermore, in the part that is covered by ice, you divide it up into thickness categories. So you might have one thickness category that's like 0 to 50 centimeters. And then you've got another thickness category that's 50 centimeters to 1 meter, and then 1 meter to 2 meters, something like that. And the entire grid cell, its area has to be covered by all of the sum of all of these fractional areas. So the fractional areas, I'm going to A sub I, you've got N sub categories, thickness categories. A sub 0 is the open water fraction. And then the sum over all of those area fractions has to be 1. Also, all the area fractions have to be non-negative. And so this constraint, this geometric constraint, means that these areas have to lie on a simplex. This is just the standard definition, actually, right here, of a standard simplex. Simplex constraints appear in a wide variety of contexts, not just CICE. So the methods I'm developing here could in principle be used in lots of other contexts, but I'm not going to pursue that. I'm going to stick to CICE for now. Okay, so the point of this talk is we're doing CICE data assimilation. We have observed the open water fraction. There's lots of other things you could observe, but just for the sake of this talk, we've observed the open water fraction. we've updated that using this scalar thing that I just talked about. And now I need to update the other model variables. And specifically, the way that I need to update the other model variables is to sample from a conditional distribution. It's the conditional distribution of the other variables given the updated open water fraction. And I'm not going to use regression, because if you use regression, it won't satisfy these constraints. Okay, so here's an illustration. I'm assuming I've got two thickness categories and an open water fraction. So open water is on the right axis, thin ice is on the left, thick ice is on the vertical axis. The white triangle here is the simplex, and allowable physical states have to be on the simplex. I've got a forecast ensemble in blue coming from the model, and then I've got a true state here, which is the green star that's kind of hard to see in the middle. And then I've made an observation of the open water fraction from the truth, and then I've applied just a standard EnKF, which basically is using regression. And you get the red dots. So the red dots are the analysis ensemble on one grid cell that comes from an EnKF, and it's off the simplex. It's producing negative area fractions, which is a problem. You can, of course, fix that problem in an ad hoc way by just projecting your ensemble back onto the simplex. And that works, and people have done that kind of thing. And it works in the sense that you can run data assimilation in this way, and you can get answers out, and the answers are not terrible. But I would like to do something that is more naturally integrating this constraint rather than just post-processing it in an ad hoc way. So that's the goal of most of this talk. Okay, I've already said we're going to observe the open water fraction. That's equivalent to observing what people call the CICE concentration, which is 1 minus the open water fraction. Skip ahead to that. I've already said this as well. So the approach I'm going to use is parametric. So it's like with an EnKF, you assume Gaussian. That's a parametric distribution. Here, I'm going to do a parametric distribution as well. I'm not going to do regression. I'm going to use Dirichlet distributions. So what is a Dirichlet distribution? Well, it's a distribution that is natively supported on the simplex. It's a class of distributions natively supported on the simplex. The parameters of the distribution are this vector alpha, which is a list of positive numbers. The direction of the alpha vector tells you the center where the mass of the distribution is centered. So I've got on the top left 3, 3, 3 centered in the middle of the simplex. On the top right 1, 2, 3 centered off to the edge of the simplex. The magnitude of this alpha vector tells you the spread of the distribution. So in the top left I've got 3, 3, 3. Bottom left I've got 30, 30, 30. The direction is the same, but the amplitude is different. And a bigger amplitude alpha gives you a smaller spread in the distribution on the bottom. You don't need to know that, but I like to give you just a little bit point of reference for what a Dirichlet distribution looks like before talking about them for the rest of the talk. Okay, so that's Dirichlet distribution. How are we going to use them? We are not going to just use one Dirichlet distribution on the simplex. Why not? So when I talked about the first step here, the QCEF thing, nope, it's not working. So when I talked about the first step, I have bounded variables, something between 0 and 1, for example. And you might be in a situation where your forecast ensemble has half of the ensemble members on the boundary. And if you just use a normal PDF for that, it is a bad fit. Because a smooth PDF is going to have 0 probability of being on the boundary. That's why I inflated the boundaries. I allowed Dirac delta distributions on the boundaries to allow for there to be finite non-zero probability on the boundary. The same thing happens here with the Dirichlet. So you can have, a bunch of ensemble members on the simplex, but then you also get ensemble members that are on the boundary of the simplex, and you get, maybe a third or half of your ensemble members are on one of the boundaries of the simplex. And if you just use one Dirichlet distribution, that's a bad representation, because one Dirichlet distribution will have 0 probability on the boundary. So what we do instead is we say, I'm going to have one Dirichlet distribution on the simplex, and then I'm also going to have a Dirichlet distribution on every element of the boundary of the simplex, because every element of the boundary of the simplex is itself a simplex of lower dimension. So I just keep using Dirichlets all the way. A Dirichlet on the boundary of a triangle here, so on the line, that Dirichlet distribution is actually just a beta distribution. But a beta distribution is sort of a one-dimensional reduction of Dirichlet. So we can think of it as Dirichlets all the way down. Okay, so this is the parametric form I'm going to assume relating the open water fraction and all the other categories. And it naturally respects the simplex geometry. The parameters are these alphas and the pi's. So the pi sub k, those tell you how much probability is in each of these classes. I didn't mention we're calling these things classes. So like the center of the Dirichlet, the center of the simplex is a class, and then each one of the sides is also a class. It would be natural to call those categories, but we're already using the word category for ice thickness categories. Okay. So pi k tells you how much of the total probability is in a given class. That's the form for the distribution, but we don't actually know any of the parameters. It's just like if you're doing an EnKF and you say, well, EnKF uses Gaussian distributions, my forecast is Gaussian, but you don't know what the mean and the covariance are until you estimate them from the ensemble. So here again, we've specified a form for our parametric distribution, but we don't know what the parameters are, so we estimate them from the ensemble. The weights are easy. You just count how many ensemble members are in each class, and then you divide that by the total number of ensemble members. And even though the total number of classes can be very large, 2 to the n cap plus 1 minus 1, which can be very large if you have, so if you have 5 thickness categories, this is like 63 classes, which is a lot of classes. In practice, what happens is that most of the classes don't have any ensemble members in them, so they get 0 weight, and that keeps the number of classes manageable. We also need to estimate the alpha parameters of the Dirichlet distributions. Those ones, we use maximum likelihood. Unfortunately, there's not a closed form analytical expression for the maximum likelihood parameter given some sample, so we have to do that iteratively. So that's a main cost of the method here, is doing the maximum likelihood estimation. Okay, so at this point, we've specified a parametric form for the joint distribution of A0 and A. The goal here of this second step is to sample from the conditional distribution of all of the other area fractions given the open water. If you take this parametric form for the joint distribution, and then you figure out, well, what would be the conditional distribution for that, it turns out to be the same kind of thing. So it's still just a sum of Dirichlets. So just like if you have a Gaussian mixture and you condition it, the conditional distribution is also a Gaussian mixture, but with different weights, different parameters. Same thing here. We have a sum of Dirichlets. When you condition it, it's still a sum of Dirichlets, but the weights have changed. Actually, the alphas don't even change, which is convenient. It's just the weights. And we have an explicit analytical expression that we can evaluate to tell you what the conditional weights are. So that's great. The goal is to sample from this conditional distribution. And actually, it's not hard to do that. So one algorithm you could imagine for sampling from this conditional distribution would be first to roll a die with weights pi sub k, and that'll tell you which class you're going to be in. And then once you know the class, you just sample from the corresponding Dirichlet. And there's simple methods for doing that. It's basically like a softmax function applied to some gamma distributions. So it's actually not hard to sample from this. We are not going to do that though. We're going to do something much more complicated. So, but why? Why are we not going to take the easy route? So we're interested in a spatially extended problem, not just one grid cell, which is what I've talked about so far. And if you just did independent sampling on every different grid cell, each individual grid cell would possibly have a good distribution, but then a single ensemble member would have no spatial coherence across grid cells. It would totally scramble up the spatial coherence of your ensemble. So we don't want to do that. So what we're going to do is adopt a transport approach. So we're going to map our forecast ensemble members to analysis ensemble members. And then if we use the same map at all grid points, then we preserve the spatial coherence in the ensemble members. So our map is going to have two parts. This whole talk is like a binary tree. You know, it's two-step data assimilation. We're in the second step of two-step. The second step of two-step we're going to do using a two-step process. I appreciate that that can be possibly confusing. Happy to try to clarify later if anyone has questions. In this part, though, the first thing we do is map from class to class. So you're dealing with an ensemble member from the forecast. In the forecast, it's in some class. In the analysis, it's going to be in some class. And we develop a map that will tell us, okay, if you're in this class in the forecast, then you're going to move to this other class in the analysis. Okay, and then once we have determined which class we're in and which class we're going to, then we do another transport map from class to class. So the first part where you, yeah, I think what I just said on the last slide was confusing. So first we map from which class are you in to which class are you in. We just decide which class you're going to be in. And then once we know which class you're going to be in, we map from inside one class to inside the target class. So for the first part, where you're just trying to determine which class you're going to be in, we use a linear programming. So we solve a linear programming problem. There's lots of ways of doing this. We've set it up so that you're guaranteed to be sampling from the correct Bayesian posterior, but you move as little as possible. So if possible, you try to stay in the same class that you're in the forecast. You don't jump from one class to another one. If you do have to jump from one class to another class, you try to jump to a class that's similar to the class that you're already in. This kind of linear programming problem has appeared in the data assimilation literature and other places. For example, Sebastian Reich has an ensemble transport particle filter that solves essentially exactly the same transport problem. But that approach is mapping from ensemble members to ensemble members, and so it doesn't scale very well as the ensemble size grows. Here, we're mapping from class to class, and the number of classes remains typically small, maybe 5 at most. So in many cases, this linear programming problem has a unique analytical solution, and we can just use it. In some cases, we have to do a little iterative descent, but it's an easy problem to solve. So this, even though we do have to solve this numerically in some cases, it's not very high cost. Okay, then we've now said you've got an ensemble member, it's in class 5 in the forecast, and it's going to move to class 3 in the analysis. So it's a sample from one Dirichlet, and we want to transform it so that it's a sample from a different Dirichlet. How do we do that? We use this expression here, and it looks complicated. I'll try to explain it. So first of all, this division by 1 minus A0 that happens on the left and the right, you can kind of ignore that. That just makes sure that everything sums up to 1 appropriately. And then we've got a composition of a forward and an inverse function, and it looks a lot like what happened in the Quantile Conserving Ensemble Filter, but it can't be exactly the same because everything here is a vector. We've got a vector of areas, a vector valued function, right? Everything is a vector, so it can't be exactly the same. So what is it? What are these functions that we use to transport from Dirichlet to Dirichlet? Well, step back with me for a minute. Forget that we're talking about data assimilation, ensembles, forget all that. Imagine that you were taking Introduction to Mathematical Statistics in the first semester of your PhD with my colleague, Will Kleiber. You've got a PDF of n joint random variables. So this is your joint PDF. you know you can factor that as a marginal times a conditional. So here's your marginal, P of x1, and then the conditional would be probability of everything else given x1. But now that conditional part, apply the same thing to that. So you say the probability of everything given x1 is actually the probability of x2 given x1, that's this guy, times the probability of everything else given x2 and x1. And then you just keep recursively factoring until you have factored your joint PDF as the product of a bunch of scalar PDFs. Now, for each one of these scalar PDFs, you can define a CDF. Okay, and then take all of those CDFs and stack them into a vector valued function. It turns out, and my colleague Will Kleiber has actually assigned this as an exercise in his Intro to Math Stat class. If you apply this vector valued function to the original random variable, the result is a new random variable that is uniformly distributed on the unit hypercube. So this is a transport from some random variable to a uniform distribution. And now, just like we did in the first step where it was a scalar, we're going to compose a forward transform to the uniform distribution with an inverse transform to the target distribution. So we map from the forecast to the uniform, and then from the uniform to the analysis. And we apply that map up here to the ensemble members to transport them from prior to posterior, from forecast to analysis. So it turns out these are triangular transport maps, which are, popular in the literature these days. So there is a connection. It's not a super tight connection node. Most of what's happening, I think, in the triangular transport map literature is mapping to a Gaussian as your intermediate distribution, and not necessarily using these conditional chain distribution, the marginal conditionals. We can only get away with this if you were trying to do this non-parametrically. It would be very hard, and I think that's why the triangular transport people have not latched onto it. They're attempting to do non-parametric approaches. We are using a parametric approach, so our distributions are Dirichlet. And then when you do all of these marginals, so if the joint distribution on the left is Dirichlet, this thing on the right, every single one of those scalar PDFs is a beta distribution, where the parameters of the beta distribution are known functions, known simple functions of the parameters of the original Dirichlet distribution. So we can actually practically implement this thing because of our parametric assumption. There is one nice thing that reduces cost. So if your ensemble member doesn't change classes, so he's in class 3 in the forecast and then he moves to class 3 in the analysis, it's not changing classes, that whole transport chain of beta CDFs and beta quantile functions, you can show analytically that it just reduces to a scaling. You're just taking the areas from the forecast, multiplying them by a number to get the areas in the analysis. Conceptually, what's going on here is, let's say in the forecast, you had a certain open water fraction, and then when you do your analysis, the open water fraction goes down. What this approach does is it just expands all of the other fractions, all of the other category fractions, so that the total sum is 1. Or conversely, if the open water fraction goes up from forecast to analysis, then all of the other area categories just uniformly go down, so that the sum remains 1. That's nice because it saves us some computation. It's also nice because it connects to something that other people in the literature have done. They've just used this. They've just said, okay, I'm only going to update my open water fraction, and then all the other area categories, I'm just going to scale them to maintain that everything is positive and everything sums to 1. So a nice sort of simpler version. Okay, it's been fairly complicated, so I want to give you an illustration to help ground you in what's going on here. So on the left, I've got a forecast ensemble color-coded by class. So the pink ones are in one class, the purple ones are in a different class, etc. On the right axis down here, the black dots, those are the values in observation space. I'm observing open water fraction, or if you prefer, CICE concentration. Now in the middle, I have updated the black dots. So I've observed CICE concentration, I've created an analysis and observation space, and then I've updated the ensemble members by just scaling them. And it works. I mean, everything remains on the simplex. You don't have to do any post-processing, but there is a downside. So if you'll look in the prior, there's nothing, there are no ensemble members that have thick ice. So up near the top of the triangle there, that's thick ice. There's no thick ice in the prior. This scaling approach has taken the ensemble members on the boundary, and in order to, when it scales them, it creates thick ice, which was not there to begin with. And so that could be problematic. The right panel here illustrates what happens with our transport method that allows ensemble members to move from one class to another. So the blue dots here that were on the boundary in the prior, they're not there. They're not on the boundary anymore in the analysis. They've jumped off because our method allows ensemble members to change classes. Okay, I'm now going to get into the actual results. So we applied this to the single column version of CICE 5. It's all CICE 5, but when you just do one grid cell, it's called Icepack. So it's not a different model, it's just a different name. We're going to use 5 thickness categories, which is the default. The single column version of CICE is not a chaotic model. So data assimilation, you know, if you use the same forcing for all ensemble members, the same forcing and the same parameters, you'll just identify the state pretty quickly, and the ensemble will collapse. You know, the spread collapses, and all the methods work well, which is not terribly interesting. It's also not terribly realistic, because in the spatially extended problem, you have all these lateral processes, ridging and breaking and stuff that don't happen in the single column model, and that would create ensemble spread. So it's great to use the single column version, but we need spread. So what we do is we have an 80-member atmospheric forcing. Even that is not really enough to create enough spread, because our 80 members are all drawn from a reanalysis, and so they're all kind of close to the truth. It's not like this ESM large ensemble where all the ensemble members are just completely different. So we don't quite have enough spread with that, so we also perturb parameters. And with that, we get enough spread to do some data assimilation. So here's what it looks like. On the left, I've got the open water fraction as a function of time for the ensemble. All the lines are different ensemble members. You can see that there's no open water up until the beginning of summer. And then when summer starts, you get a big melt. There's a lot of open water fraction, almost 1, although it doesn't melt all the way out. And then at the end of summer, just freezes right back up again. The blue line is the ensemble member that we've chosen to be the truth case, the reference case. It's not right in the middle. It's not right on the edge. It's kind of on the shoulder of the distribution. The right panel is the same thing, but for the thinnest ice category, not the open water fraction, but the thinnest ice category. Okay, we're observing CICE concentration, but we need a likelihood. So, you know, if you just give me like a number, CICE concentration, I've observed it to be 50%, I can't use that in data assimilation. I need some quantification of the uncertainty in your observation. And that's not well described in my experience in the literature, especially for CICE concentration data. So we've come up with something ourselves. We've said there's various ice observing satellites, including cryosat and IceSat. They orbit around, they look down a long track, and they take lots of along track observations where they just say, is it ice or is it not? They observe more than that, but we are only going to use the is it ice or is it not? So if you're looking at one grid cell, the satellite track passes across that grid cell, and at several points on that grid cell, it observes open water or not open water. If you model those observations as being flips of a coin, independent flips of a coin, then the distribution of the observations is binomial, and then the likelihood function is a beta distribution. So that's what we're going to use. We are going to assume that you only get 10 observations in your grid cell, which leaves you a pretty broad uncertainty in your observation. Once again, we do that because if you have very high certainty data, you just lose your ensemble spread and all the methods look the same. So not interesting. We're going to assimilate these observations every 5 days. Over 1 year of forcing data, that only gives us 73 cycles, which you don't get a lot of statistical power with only 73 cycles. So what we do is we do 5-day cycles, but we do 5 different experiments. So one day we'll start, one experiment assimilates on January 1st, one assimilates on January 2nd, etc. And that way, between the 5 experiments and the 5-day cycle, we cover all the days of the year. So we have 365 assimilation cycles. We're going to compare against just a standard Ensemble Kalman Filter. It's a deterministic one where we post-process by just projecting back onto the Simplex. We're going to compare against a standard particle filter, just a bootstrap particle filter. And then we're also going to do a method where instead of doing the full transport for the second step, we just do scaling. So we just do this thing in the second step. All right, so those are all of our methods. That's our configuration. Here's some results. So I'm showing, as a function of time, the difference between the ensemble mean and the truth. Open water fraction on the top, thin ice in the middle, thick ice on the bottom. The blue line is the free run with no data assimilation. The orange line is the EnKF, and the green line is our new method. And generally, the green line is kind of closer to 0 than the other lines, so it suggests that we're kind of doing better in that sense. The thicker ice categories, you don't really see much difference, and that's because we're observing open water fraction, and so there's just not as much information about the thick ice categories in our observational data. Okay, this is a summary across time. So different panels are different ensemble sizes. In each panel, we're showing the absolute error in the mean. So you take the reference case, compare that to the ensemble mean, take the absolute value, and then average that in time, all 365 days. The horizontal axis on the left is the open water fraction. That's what we're observing. And on the right is the thickest ice category. So if you look, for example, at the 20 ensemble member, the purple line is the particle filter. It does very poorly. The blue line is just doing nothing. It's the free run with no data assimilation. And then the other 3 lines all look the same. So the EnKF and then our filter, they basically perform the same. When you start to increase the ensemble size, though, you get an improvement. So the particle filter improves a lot. And then our green filter here is the best of the bunch at 40 ensemble members. At 60 ensemble members, even more improvement. We're still the best of the bunch. But then by the time you get to 80 ensemble members, the particle filter has jumped past us into the lead. That's not surprising. This is a very low-dimensional problem. Particle filters do well on low-dimensional problems. How this extrapolates to the spatially extended problem remains to be determined, but we do expect that our new method will give you an improvement, at least compared to an Ensemble Kalman Filter. So in the future, we're still working on this. We don't have any money, as you might imagine, at this point, but we are still working on this. We want to not just look at CICE concentration observations, we also want to look at CICE thickness. And then, of course, we also want to go from the single column to the full spatially extended. We have a manuscript that we've submitted to QJRMS. I would be happy to share that with you if you want. Just let me know. And that's all. Thank you for your time. I want to go back so I can see what you guys look like.
Awesome. Yeah, thank you very much, Ian. That was a very interesting talk, and I think very well presented too. I liked all the, thank you for the cartoons to help us get a sense of things. So yeah, so with that, I guess if anybody has any questions, I think please feel free to. Yeah, Laura, please.
All right, thanks. That was really well presented. And maybe we can talk about this in person since we're very close. But I have a lot of questions. The one thing that I did kind of miss from your presentation was I didn't make the connection. Maybe you said this and I missed it, but so your tests were in the single column models and you want to extend it to the spatially, show this method and versus the easy method captures that spatial coherence. But I didn't quite see how this method does that, and maybe I just missed it. So like on your like little triangle, how does that ensure spatial coherence?
So on one triangle, you can't see it because the one triangle is just one grid cell.
Right.
So I can't motivate it that way. But let's see. So I'm going to apply this transport map from forecast to analysis to the ensemble members at each grid point, but it's going to be in some sense the same map at every grid point. And so if you have an ensemble member that has some nice spatial coherence to it, and then you apply some function to that at every point, but it's basically the same function, then you shift the whole ensemble member, but you don't destroy the spatial coherence. Whereas if I was applying a different function at every point in space, then I might scramble everything up. I say so it's not exactly the same function at every grid point because the forecast and the analysis are not exactly the same at every grid point. But it's the same approach, right? So I'm applying the same kind of map. So hopefully we will maintain more spatial coherence than if you just did everything independently.
I see. Okay. But you haven't, is it fully going to rely on your experiment results to show how much it is spatially coherent, or do you have like theoretical basis for thinking that it will be totally as spatially coherent as the forecast?
So
does that make sense?
Yeah, no, I mean, I can't guarantee that it is going to be fully spatially coherent. All I can say theoretically is that if the forecast and the analysis are not far apart, then I will maintain spatial coherence. But if you have a big jump from forecast to analysis, then it's possible that I could be introducing some sort of spurious spatial structures, spatial variation in here. And that's kind of a hard, we have an angle where we can theoretically we know how to minimize that spatial variability, but practically we don't know how to do it.
Yeah.
So there's still work to be done there.
Cool. Thanks.
I just had kind of a question about considering melt ponds in the observation error for CICE concentration. I think if you were using like passive microwave,
Right.
Basically looks like open water. Is that something, I think Icepack has some melt pond parameterizations and other things. Have you thought about that at all, or?
I have not. Well, so I was just, like I think I mentioned, I was just in Bergen a couple weeks ago talking with them, and they're doing operational, they're doing a regional model and data assimilation, and they just don't assimilate in the melt season. Yeah, they only assimilate in the freeze and winter, but when it starts melting, they just say we don't even know what the likelihood is for these observations. We have no idea, so we're not going to do it. That's absolutely an interesting question, though, of trying to sort of come up with the likelihood. It may be informed even by the model variables because you've got melt ponds, but it's not something that I have thought about myself.
Okay, yeah, it's definitely a difficult problem.
Yeah.
Concentration retrievals. Okay. Any other questions that?
I have a maybe quick one. If
Yeah,
does.
please.
As you were talking through this, I was wondering if there are applications to specifically when you were talking about how it's not a chaotic model. I was like, oh, land models are very similar, and maybe I wonder if a similar approach could be used because they have similar like categories and things like this. I don't know if you've thought about that at all.
A little bit, yeah. So I'm sitting here in the data assimilation DARES group at NCAR, and they have a land modeler here doing data assimilation, and they've kind of said, oh, there's probably some synergies, but I haven't really followed it up. But then 2 weeks ago in Norway, I was at the EnKF workshop, and there was a student presenting. I don't remember what university she was from, but she was doing data assimilation for land models, and she was doing water assimilation. So I guess in each grid cell, there's a total water content, but then the total water content is also split between different categories of like surface water, deep water. And so it's a simplex constraint, but it's not the standard simplex. You don't sum to 1, you sum to some value. But that's quite straightforward to handle within, that's not a difficulty. It's very close to what we're doing. And she was using just scaling. And she found actually that just scaling was actually significantly worse than doing an EnKF in post-processing.
Oh, interesting.
Yeah, which surprised me. But I do think there's potential to adapt our method for that application, but I haven't followed it up.
Yeah, cool.
Yeah, that actually just makes me wonder if there's any relevance for fire modeling at all, if there's sort of categories of combustible materials or things like this. I don't know that much about them, so I guess, yeah.
I don't know. I don't know anything about fire models really, so I can't say.
Something
Yeah,
we'll have to.
that people get that I've mentioned to people because it sounds exciting is that epidemic models like SIR models,
Yeah.
susceptible, infected, removed, or recovered, the total population doesn't change. So you have all these categories. So actually all those epidemic models are living on a simplex. And we did a Dirichlet mixture where you put 1 Dirichlet on the simplex and then 1 on each side. You could also do a clustering where you say, no, I've just got my triangle, but instead of putting 1 Dirichlet on that, I'm going to put like a few, and that way I could deal with multimodal stuff on the simplex. And you could do that within our framework. It's basically just still about a sum of Dirichlets. So it basically wouldn't change anything. But we haven't pursued that.
Yeah, that's really interesting. I'd use some ESMDA stuff with like an age class model for COVID. Each age class had different susceptibilities, and sort of, yeah. Wonder if that, yeah, anyway, really interesting to think about for sure. Okay. Any other questions for Ian before we?
Well, you know where to find me. So if you have any questions, I'm here.
Sure, and I'm sure there were some people who might not have been able to make today that might want to.
Monday, normal time.
Right, yeah. So if that's okay, I'll let them know they can do that maybe.
Yeah, sure.
Okay, great. Okay, well, yeah, with that, thanks everybody, and see you next week.
Thanks very much.